So lest we forget, let's go through our labs, understand what the principle behind the labs were. Because so, we did the density lab, and that was just kind of physical properties, right? But when we did the magnetism lab, what were we looking at? What was kind of the whole diamagnetic and paramagnetic? And what does diamagnetic mean from this side of the room? Anyone? What is paramagnetic or diamagnetic? Y'all gonna have some finals. Y'all need to remember this stuff. All right. So paramagnetic means you have an unpaired electron, and it means that it would attract the magnet with the salt. Diamagnetic means that it had two electrons. Means it had paired electrons, which means it didn't have a magnetic moment and it didn't interact with the magnet, right? So we started looking at, are the magnets paired or unpaired, right? Then the next thing we looked at was whether something was ionic or covalent. So the whole point of that was to say, hey, are we sharing electrons or am I releasing electron and becoming charged, right? So we went from paired and unpaired electrons in the cloud around the atom to sharing or transferring electrons. And then the next thing we looked at was, I think, polarity. We started looking at, we did the electromagnetism lab. So we started looking at whether the bond was nonpolar covalent, polar covalent, or ionic. We used electron negativities for that. And then, come on, I had a head wound like a week ago. What was the next lab after that? I think we did molecular geometries after that. Like chemical and molecular geometries comes next. So we went from paired or unpaired electrons being where all the magic happens in chemistry, where we're getting reactivity. We started bonding, we started transferring them, we started looking at whether they're polar, then we started looking at whether the whole molecule is polar. So you can have polar bonds in a nonpolar compound, you can have polar bonds in a polar compound, because the geometry would either cancel out those polar bonds, the dipoles, or they wouldn't, right? Then last week we started looking at what's happening between the molecules. And we identified that your intermolecular forces can be where you have a dipole, hydrogen bonding as your strongest force between nitrogen, oxygen, fluorine with a hydrogen on it, and another nitrogen, oxygen, and fluorine with a lone pair of electrons. Dipole interactions between polar compounds. Polar dipole interactions and induced dipole interactions between polar and nonpolar. London dispersion between nonpolar and nonpolar. And we remember that nonpolar London dispersion forces happen everywhere, but as you go from the nonpolar interactions up to the ionic interactions, you increase your strength of interaction, right? And then we talked about how that's going to be the cause for whether something is viscous or not viscous. This is where we start deciding whether something is a solid, a liquid, or a gas at room temperature. We start deciding whether its boiling point is, which is kind of what we're doing today with the evaporation lab. We start looking at the densities. We start looking at the miscibility, whether they can mix together, whether they can't mix together. Like everything that we think of in our chemical world starts happening between those molecules, right? Right? We good? So today we're still going to be talking about intermolecular forces, but we're going to dive in on basically the boiling point. So we're going to take, what's the best way to do it? I think I'm going to go through with the lab with the procedure, and as I walk through the procedure and we walk through the lab report, that'll kind of cue me when I need to go up to the board. So, all right. So for today's lab, what we're going to be doing is you've got this long thermometer. We have a long thermometer, and you've got 6 compounds here. One of them is acetone, and what is acetone typically used for in our society? Nail polish remover. Then you have 5 alcohols. You have methanol, which will embalm your liver if you drink it. You have ethanol, which, it's kind of funny. If you look at the NFPA diamond and you read like the risk, it will tell you that ethanol is a reproductive toxin for the skin labs. So there's also 3 samples over here. Reach into your drawer and hand me your large beaker. Okay. So these 6 here, then you got 3 over there. Here's how we're gonna do it. So you are going to take your chem wipe and you're gonna fold it 3 times or thrice if you want to use a fancy word. So 1, 2, 3. We'll see how well I can do this without a thumb. All right. Then you're gonna get this bad boy in your magnet. And however you do it, don't even laugh. Roger, I ain't playing it. So you're gonna roll, you're gonna find a way to wrap your paper around your little wand here, and then you're gonna, rip me off a piece. Come on, I got no thoughts for you. What are you gonna do? Come on. All right. And then you're gonna get yourself a piece of tape. And you're gonna dip this in your alcohol. No, first back up. You're gonna make sure this thing is on Celsius. This thing's on Fahrenheit right now. Make sure it's on Celsius. Get your initial reading. And then you're gonna dip it in the alcohol and you're gonna set it, and I recommend sitting it in there because we can actually control the environment. If we hold it up in the air, you're just holding something for 2 minutes. If you sit it in there, you can let it rest, and you have like 3 worksheets, 3 data sheets where you do like skeletal structures or whatever. You can be doing a lot of your lab report in the 2 minutes that these things are evaporated. Because you got 7 of them that you're going to do. That's like there's 9 of them you're going to do. That's like almost 20 minutes that these things are going to be evaporating. Don't stand there and discuss like the Israeli revolts. Get your worksheets done, or else you're going to be doing this later on. And we're going to do it exactly for 2 minutes. So before you get started, I'm going to put a clock up on the board, because these are the solvents that will that will like dissolve your iPad screens. I don't know about the other one, Android, but I know that like if you have like a newer Apple product, you will melt the surface, not melt, you'll dissolve the surface. So this is a good time to make sure your phones are put away. We'll use the timer up there. You're going to do exactly 2 minutes because we're trying to control the test.
Factors of the lab.
There's a word. Yes, whatever. Like, it's not back yet. I go to my concussion physical therapy on Wednesday. Hopefully I can recover these words. But you want to control the factors as much as you can, because some of them might still be evaporating past 2 minutes, but you want to have a fixed time of measure for all of them. And after 2 minutes, you'll take your final temperature, and then you'll throw this into that bucket right there. The ones out here, you can throw away in there. The ones in here, there's 2 buckets. I'll do one of these buckets over. So the ones in here can be done in there. The ones in there can be thrown away in there. Otherwise, throw them away. And and then you'll be measuring your initial temperature minus your final temperature. All right. So let's do a thought experiment. Make sure that we can figure out what's going to happen today. So you have a solvent like acetone, and the fact that you can smell it, like if you ever go into a nail salon, it just smells like acetone in there, right? That means it's evaporating. It's filling that head space, right? And they'll create a certain head pressure before it quits evaporating. If you have fans on, it's just going to keep evaporating, you're going to keep smelling it. So the fact that it's evaporating means, or the fact that you can smell it means it's evaporating, okay? It's becoming gas. So let's say the room is 72 degrees, okay? So there are gas molecules running around at 72 degrees, and when those gas molecules hit your skin, they're transferring 72 degrees worth of heat into you. If it's hotter outside, you feel that because the gas molecules have more kinetic energy and they're hitting you harder, right? So there's a certain amount of kinetic energy in the room because of the heat in the room, right? So that same heat is going into these molecules. So all of these molecules have access to the same amount of heat. But how do I want to say this? For a molecule to leave a liquid and become a gas, what is it overcoming? What are we breaking? What is that gas doing? As a liquid, what are these? So what's holding the liquids together? Intermolecular forces. So all these molecules are being held together by their dipole-dipole interactions, by their hydrogen bonding interactions, by their dipole or by their London dispersion forces, right? So the more forces you have holding these molecules together, more of that heat, let's say if they're weakly held, you might only use 20% of that heat for something to go from a liquid to a gas. Something that has like a lot of hydrogen bonding, maybe you need to use 80% of that heat to break those intermolecular forces for it to become a gas. So the more weakly bound together they are, the more easily they become a gas, and more of that heat exchange goes with them. All right, and you'll see that on your thermometer. So if something is weakly bound together, you should see a larger temperature change, because less of the heat in the room was used to break that molecule free from the liquid, make it a gas. The more tightly, the stronger the intermolecular forces are, the more heat goes into breaking the intermolecular forces before the rest goes off. Does that kind of make sense? And you can kind of think about this, like if you've been swimming and you get out of the water, you know what like the breeze feels when it goes across you. But if you've ever had like alcohol in your skin, like that's cold. When it's evaporating, it's typically like a cold. Acetone in your skin typically feels cold. Water in your skin may feel cool, but not cold. Do you see what I'm saying? Can you see how, can we staple this into something in our tangible world? Is this making sense at some level? If it's not, let's have a conversation. Is there a question why the weaker the intermolecular forces, the greater the temperature change? Timothy, how you doing with it? You all right? Annabelle? Sure? Got it? Okay. So, all right, let's go through, that's pretty much the procedure.